Flip classroom video for WJC A-Level Maths Unit 3 Pure M2.3.7 D4 Repeated Integration by Parts. So it's possible to get a two-step repeat. In other words, you have to do integration by parts more than once. And it's relatively easy to consider situations where that will be the case, but I'll just work you through an example. So if I consider something nice and easy like x squared sine x with respect to x, I would again in this particular case choose to differentiate the quadratic function and integrate the trigonometric function. But you can see already where it's going to lead me. So if u equals x squared, dv by dx equals sine x, du by dx is going to be the differential of x squared, which is 2x, and v is going to be the integral of sine x, which is minus cos x. I personally like to always put it down like this, so I'm clearly showing that I've got the uv, but I've said that before. So the integral of x squared sine x with respect to x is equal to minus x squared cos x. You notice I put the minus outside the x squared term, just so that it doesn't get confusing, minus integral minus 2x cos x with respect to x. And I've put the du by dx term at the front of this, again, just for it would look a little bit untidy if I had minus cos x 2x, but it doesn't make any difference. I could use brackets if I wanted to. So clearly I can take out the constant 2, and because it's a minus 2 it'll become a plus 2 out the front there. So what I've got so far is minus x squared cos x plus 2x cos x. That again is another integration by parts. It's a function in x multiplied by a trigonometric function. So I've now got to integrate x cos x again. Be consistent. If you chose to differentiate the algebraic function, you must consider to do it again, because otherwise you'll end up with 0 equals 0, which is not good use of your time. So if u equals x in this particular case, you can clearly see what's going to happen here. dv by dx has got to be equal to cos x. So my differential of x is 1, and my integral of cos x is straightforward sine x. So my integral of x cos x with respect to x is equal to x sine x, uv minus the integral of 1 times sine x. And I needn't put the 1 times there, I'm just doing it for completeness at this stage. So I could just actually write sine x if I chose, and the integral of sine x is minus cos x. I've been there before, done it again. So I've got x sine x minus cos x, and I could go straight in there, right? That's plus cos x if I wanted to, but I'm just being precise. So therefore now I've got to put this in. So I've got, and going back and substituting in this blue bit, you can see from the color codes that I've got here, the integral of x squared sine x with respect to x is minus x squared cos x plus 2 times that blue bit x sine x plus cos x. And if I plough that through, minus x squared cos x plus 2x sine x plus 2 cos x plus a constant. You notice I've introduced a constant now. Didn't have to, but the earlier I get it in there, the better. Okay, and again, I can clearly see that I've got a cos x common factor. So cos x bracket 2 minus x squared, if you want to write minus x squared plus 2 by all means, but I would personally write 2 minus x squared. It's less to write, and as you will see, my writing is not the greatest, plus x sine x plus k. So there is a potential, and there is one particular set of questions which are much loved by examiners. It's one of my favourite integration by parts questions, but it's a potential to repeat ad nauseum, and ad nauseum means until you're actually sick of it. Some people call it repeating to an infinity, but we don't want to do that because infinity is too hard for my brain to cope with. Integral of e to the x cos x. Now in this particular case, I can differentiate e to the x and I can also integrate it. I can differentiate cos x, and I can also integrate it. So it doesn't matter which one I choose to differentiate and which one I choose to integrate, because neither of them become any particular or any easier when I do one or the other. So I've got to choose, and I would choose, simply because it's the first term, e to the x is equal to, there's my u term, and my dv by dx term by that token will be equal to cos x. So I differentiate the e to the x when I get e to the x, and I integrate cos x, which will give me sin x. So I plug it into my equation. So the integral of e to the x cos x with respect to x is equal to uv, e to the x times sin x, minus v du by dx, which is e to the x sin x with respect to x. And that's another integration by parts. So I'll plow on and do that in a different colour. I wouldn't do that under exam conditions, but I would do it as a separate integration. So the integral of e to the x sin x with respect to x, again, be consistent. If I chose to differentiate my e to the x function, I need to differentiate my e to the x function again, otherwise I end up with naught equals naught, which is true but not helpful. So if u equals e to the x, dv by dx has got to be equal to sin x, and hence du by dx is equal to e to the x, and v is equal to minus cos x. And watch these minus signs, they'll catch you out. So this will become uv, which is minus e to the x cos x. Again, notice I've put that minus out the front there to prevent any confusion. Minus integral minus e to the x cos x with respect to x. And this one will give me minus e to the x cos x plus, because of that minus minus combination, e to the x cos x with respect to x. And some people at that stage go, oh, there's another integration by parts again. And I could just keep on going and going and going. And all I'd do is I'd be keep on cycling round and round and round. So the thing to do here is to put it back together again. So the integral of e to the x cos x with respect to x is equal to the e to the x sin x from my first run through of integration by parts, minus, notice that bracket coming in here, because that minus has got to distribute my result of my second integration by parts. So minus bracket e minus e to the minus e to the x cos x plus the integral of e to the x cos x with respect to x. So now that minus distributes, so it will become a plus e to the x cos x minus e to the x cos x with respect to x. Now if I add e to the x, the integral of e to the x cos x to both sides, on my left hand side I'll have two lots of the integral of e to the x cos x with respect to x. And this is the big trick, isn't it? So on my right hand side I'd be left with the e to the x sin x plus e to the x cos x. So what I'll end up with here is that the integral I wanted has got to be a half of that. So the integral of e to the x cos x with respect to x is e to the x, pulling the e to the x out as a common factor, over 2, because of that halving, sin x plus cos x. Now, I can't really simplify that, and because I didn't put any limits in, plus k.